Welcome to another video explaining the universe using the particle model. Today's video is titled The Ultraviolet Catastrophe. If you are not familiar with that problem, I will attempt to explain it right up front once we start the video. But first, a word about the book that Dave and I have written. Yes, that's the logo for our book. The large apple represents G1 gravity or Newtonian gravity, and the smaller apple inside represents G2 gravity, a lower level of gravity, which is responsible for a lot of the functions in electronics and magnetics and light and whatever. You can buy the book from Amazon in hardcover, paperback, or ebook. And Dave and I are doing a few videos on Saturday morning covering the book. In particular, I'm doing them on electronics, and my next one will be on the diode and the transistor. So we move on to the ultraviolet catastrophe. This is a diagram showing the black body radiation out of a black body, and the measured values are taken at different temperatures, 300 K, 400 Kelvin. This is in degrees Kelvin. These are the measured values, and what they're measuring is the spectral radiance or intensity or energy, and they're plotting it against the wavelengths, anywhere from 3 micrometers down to 0, although 0 can never exist as a frequency. The problem comes that in classical theory, the equations developed for classical theory predict a curve like this, which keeps going all the way out to almost infinity, almost to 0. And it doesn't show this falling off, and it falls off right around the ultraviolet range. And that's why it's called the ultraviolet catastrophe, because classical theory doesn't explain why the fall off, it doesn't explain the fall off at all. So let's talk a little bit about black body radiation. There's 3 black bodies. Lady has put 2 of them up here. This is from a video. And this is with the room light on so that you can see the boxes, and you can see that there's a tiny hole drilled in the front cover of the box, and it's black. Okay, no light being reflected off of or coming out of the body. And the box has a hollow cavity. We'll get into that for a moment. But what this is set up to do is to turn the room light off and look at these 3 boxes using an infrared detector. And that's what we're going to do here next. And this is what you see. What you see here is the box, the surface of each box emitting infrared. The reason it's doing that is because the atoms in the box, even on the surface, are vibrating and pushing out infrared type light just from the heat. Okay, and now the black holes are not so black. There's a lot of infrared, higher intensity infrared coming out, even though under normal conditions we see it as a black hole. Turns out that there is visible light coming out, but it's such a low level that our eyes don't generally perceive that. Okay, so here's a little bit more about the black body itself. The whole idea is that light bouncing off of here, when you look at it infrared, you don't see it, but the light will come through in and bounce around until it's gone. The theory being there is no light coming out of the box because it gets trapped inside. Now, but inside, just like on the outside, this picture shows photons. These are photons inside the cavity being emitted from the surface and then bouncing around just like it shows here. And then eventually some of them come out the aperture, and you can either look at it with your eyes or you can measure it with an instrument. And that's, of course, what they do, is measure the light coming out of the aperture when you heat it up to these different temperatures, and you can plot those curves that we talked about. Okay, so classical theory does not explain the ultraviolet. And I'm just repeating this and to point out, you do get visible light coming out when it's heated up very hot. Even though you might not see it with your eyes, it's sensitive enough to be measured. Now, the classical theory, one of them, there's a couple of these, and one of them is the Rayleigh-Jeans. I'm using that because this is what the curve says. This is the Rayleigh-Jeans law. You plot this equation and you get this curve, and it goes all the way up to almost infinity. And this equation is a function of frequency and temperature, capital T meaning Kelvin. And then this is basically a constant here, except for the frequency is squared. This is Boltzmann's constant, and this is the temperature, and this is in terms of the change. As you change the frequency or wavelength, and here you can express it in terms of wavelength, but it ends up generating the same curve, and it doesn't predict the fall off. So this is the ultraviolet catastrophe. Science is now looking for the answer. Why can't with classical equation get the answer? Well, Max Planck steps into the picture in 1900. He develops his initial equation where temperature is not included. And many of you have seen this energy of the light is equal to Planck's constant times nu being another way of saying frequency. And he does this, he applies this to the black body radiation. Does not solve the problem either. So he's stuck with his first equation. But then he thinks it through, and this isn't really a too far off anyway. Planck then discovered that he could derive a better equation, but only by making what he considered to be an outrageous hypothesis. For a mode of frequency, for a given frequency, the energy in the cavity can only exist in lumps or quanta of size E equals HF. This is what he's calling one quanta. HF is one quanta. And so how does this avoid the ultraviolet catastrophe? Here's some logic, and this is a part of the logic. It's not too bad. Even a single quantum, even one HF, for a very high frequency, short wavelength, would be huge. Even the mode would be huge. There would be a lot of them. The chances of great chunks of the available energy going to more than a few high-frequency modes were remote. It's just logically saying, if this is huge, in his mind, the one quanta is huge, then if you have a huge quanta of energy and it's got to exist with a high-frequency, small wavelength, probably couldn't happen. Doesn't explain why, but we'll get to that. But he makes this outrageous hypothesis, and when he does, what he does is he takes his equation, he adds n into the equation, n meaning being an integer. He's saying that all energy only exists in discrete quanta. You either have 1 HV or 2 HV or 3. That's the only way it exists. He's saying energy isn't continuous. It's a little bit, I don't quite agree with that, because energy is a man-made definition. It's not real. Between 1 and 2, there could be an infinite number of energy levels. Between 2 and 3, another infinite number of levels. He's excluding all the ones in between, and he's only using these. It's like he's sampling and throwing away a whole bunch of energy levels, allowing only integer values of n, and he fixes the problem. The curve now matches the measured values. But there's no physical reason, except the reason he was talking about, where the probability of these large quanta working with a narrow wavelength probably doesn't happen, and he excludes them somehow by doing this. So let me change the subject a little bit. Is light real? I just talked about energy. Is energy real? And my answer to that is yes. Light is real. Light from the sun hits our body, heats up our skin. That is, the light causes the atoms in the molecules of our skin to vibrate faster, and that our body senses that vibration, sends a signal, and we feel the heat. And it takes a physical object with some size and mass to do that. Saying light is not an abstract mathematical function. It's a real entity, a physical particle, if you will, a photon, if you will. Or, of course, if you've been following the particle model, you realize that the TPM light is a physical model. But let's go back. What would Rayleigh use? What would Planck use as their model for light? What did they have? Newton's corpuscles? That's been pretty well rejected. It is a physical model, but it's been rejected. It doesn't work in many cases. Maxwell just recently defined his equations and came up with the electromagnetic wave theory. And yeah, there's a model of vibrating charges here, plus and minus vibrating, causing an electric charge, blue going vertical, magnetic field following the electric field. And that's what they say it is. Is it physical? What are fields? What is an electric and magnetic field? They never tell us. It's one of David's famous questions. Well, just tell me what a field is. And they don't say so. Don't know that Maxwell or Planck actually had a physical model to work with, but he did talk about large chunks of energy that would be excluded at high frequencies. Well, the TPM light, yes, that's a stream of peaks spaced at given distances. So here's a peak and there's a wavelength between the two is peaks. Could be any color light here, steady stream. G1 particles, basically the size of an electron, but no charge, moving at speed c1, which is close to the speed of light. You can make this any waveform you want to out of this stream by having more here and almost none here, and you create a peak here and a peak here and a valley. You can make sine waves, triangular waves, whatever you want. Nonetheless, there are physically G1 particles grouped together at a peak. The more G1s at the peak, the higher the intensity. The closer these peaks are, the higher the frequency, the shorter the wavelength, and the opposite is also true. Okay, so now instead of photons, and I just put this again just to show you that inside this black box, you get radiation. You heat this thing up very hot, you got vibrating atoms. TPM is going to push out peaks of light. Peaks of TPM are emitted, bounce around, and every time they hit, they lose G1s and exit. Some of them finally, at low intensity, exit the aperture. By the way, the inside is coated with carbon black. That's soot. And it causes a very high absorption rate, which it just sounds like it's deliberate. They want this to get down to a lower intensity. And even though you see the curve go way up and come down, we're still talking about overall, very low intensity. Because one hit and you lost 98% of your signal. That's quite a bit. Okay, so now I'm going to talk about how the TPM might explain the ultraviolet catastrophe. I'm going to start with describing, here's a peak. I think there's maybe almost 20 G1s there. I actually tried to count them, 10 here and 5 here just to make nice numbers. And I'm going to draw a big circle for a large peak and a smaller circle for a medium peak and then an even smaller one. And intensity of the wave generally is the number of G1s at the peak, although it does include all of the G1s in the stream. All contribute to the energy that can come from light, for example, hitting your hand, your arm. Okay, so now I'm going to take this high intensity, this one, and I'm going to space it out at some wavelength. That's an arbitrary number, but the wavelength goes from here to here, and this is high intensity. You got a nice wave here. You should be able to see this, high intensity light. But here's one of the problems, and this is where I think what Planck was trying to say, but without a model, he wasn't drawing a picture like this. So I'm going to take two high intensity peaks, 20 of them here, 20 of them here. I'm going to put them so close together there is no spacing. If you don't have a spacing like up here, you don't have a wave. All you have is a stream of 20, 20, 20, 20, 20 peaks in a steady stream, almost like electricity rather than light. You got to have some spacing. So, okay, maybe you can move this apart a little bit more until it does become visible. But you can't see this with your eye, and you probably can't detect it with the detector because they're looking for waves as well. And in order to have a wave, you have to have two peaks and a space. But when you get down to low intensity, which is what comes out of the aperture, very low intensity, then you can be at that same wavelength of 50. It is visible to the extent that this is enough to intensity in the first place to trigger your eye or trigger the detector. But the fact is, when it gets low enough of intensity and close enough together, you can't see it, you can't detect it. And that's why at low intensity, high frequency, short wavelength, the spectral energy comes down towards zero. Okay, I think this is just I know what I was going to, I forgot what I was going to do here. Infrared, I'm going to apply this now to this chart, specifically the measured values. Start with the infrared. This, even though this overall is low intensity, this is really low intensity here. But it could have a very high or medium peak at a wide wavelength, so there is a frequency there. There is something to measure, but the reason it is small is because the wavelength is so big. The bigger the wavelength, the fewer times that light can cause the energy, like heating up your heart. So the hits are very slow, whereas the higher the frequency, it hits faster, heats more. So it's because the wavelength is so long that this stays low, even if the peaks were high. So this starts out low and stays low in the infrared. In the visible, well, in the visible now you can have a medium intensity and a frequency or a wavelength in this range, and it can be visible, or if it isn't visible with the eye, at least visible with measurable with the equipment. But when you get to the ultraviolet, you find that the only way you can have any frequency down here is to have a low intensity with a very small wavelength. It has to be low intensity. If it's a high intensity, you can't see it. The fact is, something like this could be coming out at the ultraviolet range, but you can't see it. You can't measure it. But it could be there. What you do see and measure is low intensity. And that's why it falls off. Quite interesting. Okay, so classical theory did not account for the intensity and size of light. That's the problem. They don't have it in the equation. Intensity is not in the equation. The size of the particle, whatever it is not there. And without a model, how would they know? I mean, you have to give them a little bit of credit there. Had the classical theory accounted for intensity and size of the light, there would be no ultraviolet catastrophe. If they had a physical model 120 years ago, they would have been able to do something with at least the conceptually, even if the equations couldn't quite get there, if they didn't figure that out, because that's tricky. But there would have been no catastrophe because they would have been able to analyze it the way I just did with TPM Light. And quantizing is not needed. Max Planck arbitrarily added quantizing, got results that measured values, and he admitted it was just a shot in the dark. He had no specific physical reason except that logic about a quantum having a big chunk of energy. And I'm repeating a statement, even a single quantum for a very high frequency mode would be huge. The chances of great chunks of available energy going to more than a few modes were remote. And these greedy modes were priced out of the market because he quantized his equation. He just sampled at specific energy levels and threw the rest away. If science had accounted for the intensity and size of light, there would be no quantizing, and that's what started quantum mechanics. There'd be no quantum mechanics. Well, they may have got there anyway with other things. I mean, Einstein got into it, Niels Bohr and Heisenberg, they're all in there talking about different options, coming up with the Copenhagen Agreement. But basically, they could have explained it without quantizing, and therefore it would have slowed that whole process down. So the conclusion. Well, first of all, I get it. The ultraviolet catastrophe occurred when there was no real model for light. I might have done the same thing, but now there is a model for light. TPM gives enough physicality to provide a better answer. One possibility is that I use TPM to generate an equation for the spectral energy, which includes the intensity and size of light. Well, this isn't exactly my forte here, but maybe someday I'll tackle that problem. My plan, however, in the near future is to work on some experiments. I'm going to do an experiment on a magnetic field to show that it's a spiral, not a circle around a copper wire. It'll be a modified Oersted experiment. I hope to get some equipment to do a double slit with a detector so I could have an adjustable detector and show the effect of the effector, of the detector on the interference pattern. Some things I plan to do in the future. My name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask particle.